All right, last main one of these. I'm going to make a video about capacitors today. Hopefully help some students finish up some last minute ideas, getting ready for the AP exam. This is intended as review, not necessarily as instructional, but I'll try to go through some more or less missed details. First thing I want to talk about with capacitors is just determining the total capacitance or the equivalent capacitance. And you want to initially start with either a set of series capacitors or a set of parallel capacitors. So I've got the two Kirchhoff's laws that we'll be using, the loop rule, which is a conservation of energy, and the junction rule, which is a conservation of charge. More or less, we're either going to be focusing on the voltage or the charge in this case. So V stands for the voltage or the potential difference. Q stands for the amount of charge stored on a capacitor, and C stands for the capacitance of capacitor. There's a statement K depends on the area of the plates, the distance between the plates, if there's a material between them, a dielectric, which we'll talk a little bit about briefly as how that affects the difference in capacitance. And then a constant as well, in addition to the dielectric. So what I'm going to do first is just do the loop rule. The way I think about doing the loop rule is just drawing a loop. So here's my voltage supply. Let's say it has some voltage V, and it's going to loop through. Some's going to be there. We're going to go through here. We're going to go through here, all the way through. And what I would say is the voltage input minus the voltage output minus the voltage output equals 0. So V in minus V equals 0. When I think about it that way, I then would say, to set it up to look more like our total capacitance statement, I would say the input voltage would equal the voltage in the first capacitor, and this would be the second capacitor. So C1, C2. 1 plus voltage 2. With that now being known, I take this and I use the statement I got from the formula chart. This is very similar to how we would do it for a series circuit or a parallel circuit for resistors, except that it's not V equals IR, it's V equals Q over C here. And I just plug that in over here because the amount of charge based on in a capacitor depends on the amount of voltage supplied to it, how much pushing, the energy almost that you're giving per charge, and then the amount of charge it could hold. That would dictate the amount of charge that you could store on the capacitor. Then what I would do is plug that in. So I'll do over here Q over C equals Q over C1 plus, I'll put a T here. I like to call it total. Some people call it equivalent. Q over C2. What we want to think about here now is how does this Q compare to this Q compared to this Q? And wonderfully, they are all equivalent. I'll go through that here shortly. But this Q and this Q and this Q all reduce to 1, leaving us with a statement that says the net capacitance, the total capacitance of a series of capacitors is equal to 1 over C1 plus 1 over C2. Notice that that's very similar to how we set it up with parallel circuits and with parallel resistors. So you can think about that. This is also located on the formula chart. It has some things associated with it. Just to think about it real quick, when you have a capacitor in series, these charges will flow from high potential to low potential. So we take our battery or our power supply, and more or less there's more potential energy for this positive charge right here than there is right here. So what happens is you can think about it, either one moves from here or actually a negative charge could move from here. It's really just a shifting of one charge. There's a ton of charges located inside of this wire. So it's not that they move very far, it's just they shift over one. They just push the one next to them. So using the conventional flow of current, you'd put a positive here. As a result of putting a positive here, because it went from high potential to low potential, this would polarize, making a negative charge. It would pull a negative charge to it, and it got that negative charge from over here, so that's positive. And over here, it would pull a negative charge to it. This would happen independent of each capacitance. The capacitance of these capacitors wouldn't matter because every time I get a negative here, it had to have come from here. So we just start looking at it like this. And you could say that I have two positives here, two negatives for 2Q. two positives, two negatives, 2Q. So each of them has the same amount of charge. But then how do we think about it being a total amount of charge on it? The way I think about it most effectively for me is I just cover up the middle of it. And if you take a look at now the larger capacitor that's formed because of those two, you still see that we have a total amount of charge of 2Q, two positives on one side, two negatives on another. So that's a nice way to think about the Q's are equivalent to all of these and reduced to 1, leaving us with a statement that looks like that. So just an aside. When you go over here to junction rule says the amount of charge that moves through a circuit must be conserved, meaning that whatever charge leaves here goes here or here. So I draw one loop this direction, and I draw another loop. It could go that way or it could go this way. So when you think about it now, what you want to keep in mind is that our junction rule would tell us that the Q total, the Q that left my battery, minus the Q that was deposited on this first capacitor, minus the Q that was deposited on the second capacitor, will equal 0. What you would have done with this in previous, with just resistors in your circuit, is you would have just used current to describe that, because you're using current as just charge as a function of time. So this is our input. And then this is the charge 1 in the first capacitor. It doesn't matter what you number these, and this is the charge in the second capacitor. What I then do is I just say Q input equals Q1 plus Q2. Notice that the amount of all that would become equivalent here, because it's in parallel from our earlier understanding of just resistor circuits, is the voltage in each branch would be equivalent. And that comes from loop rule. So this loop uses all of the voltage, while this loop also uses all of the voltage. So you can also apply a loop rule there if you want. What I then do is I take my statement for a capacitor relating the charge and the voltage to determine the capacitance, and I plug in now VC. You could also call it CV. VC is a very popular card game amongst my students. So then I just say V1C1 plus V2C2. And this would be our total capacitance right here. Notice that we have C plus equals C plus C. But what are we going to do about these voltages? Well, it is in parallel. We can use the loop rule to say the voltage input minus the voltage output equals 0 for each of these loops, meaning the voltage here is equivalent to the amount of voltage here is equivalent to the amount of voltage here. So we can reduce those to 1, leaving us with a nice elegant statement that looks like resistors in series. The total capacitance for a parallel combination of capacitors is equivalent to the one capacitor plus the other capacitor. And there's a derivation of that using Kirchhoff's laws. Sometimes they might ask you, I was working through a problem yesterday with a student in my AP Physics 2 class, and it referred to using a conservation of energy statement. So you needed to make sure that you pulled this out, and you wanted to pull that from Kirchhoff's laws, where you have the loop rule, which is conservation of energy, and the junction rule, which is conservation of charge. These allow you to prove why circuits do what they do. And occasionally the College Board could ask you to use Kirchhoff's laws. It could ask you to use the loop rule, the junction rule, or conservation of energy statements, or conservation of charge statements. All of those are things that you want to be aware of and comfortable with. I messed up this year with my AP Physics C class, and I talked about the loop rule and I talked about the junction rule, but I didn't ever refer to them from their parent group of the Kirchhoff's laws. And the test question asked them to use Kirchhoff's laws, and lots of my students were puzzled. So I had to do an adjustment to that. How does this work if we have a combination of combination circuits? So we have not a series or parallel, but a series and parallel combination circuit, if you will. So let's just do a basic example. Oops, it's supposed to be there. I tried to reduce the amount of errors by pre-populating some of this document, but I know that I'm still going to have to do a few things. I identify this to be two types, parallel, but inside the top parallel branch, I see that we have a series combination. So what I want to do is I want to do a total amount of this. So I identify it first to be parallel in nature. So it's parallel in nature. So I just do this, C total equals, let's call this 1, and we'll call this 2, and we'll call this 3. I need to figure out what the total capacitance of this parallel, this series is inside of the parallel branch. So I do that by going over here, down here on the bottom left, and I would first say 1 over C2 plus 1 over C3 to the negative 1. And now that tells me the total capacitance of this, but then I understand that to be in parallel with this. That's why I flipped it to the negative 1. Notice that if I wanted the total capacitance, I must flip both sides, plus C1. And now we've got our total capacitance of it. Very similar to how you would find the total resistance of a series and parallel combination resistor circuit. So how could you do it? You use conservation of energy, conservation of charge. It helps to know which one it is. Brief description there. Voltage is the same throughout. There you go. Total capacitance. Next, I just want to talk briefly about dielectrics. It might ask you a simple question that you have to talk about. Why does a dielectric affect the amount of capacitance, the amount of charge a capacitor can hold? So we got some concepts here. So dielectric is just a block of material. It doesn't allow current to flow. So I left a space here, but it would actually be touching. You might roll this up between your two parallel plates. The dielectric I use in the lab for my students it's just paper. They used various amounts of sheets of paper to figure out some values associated with capacitance. That's one of the options they have. When it's uncharged, this is neutral, meaning it has the same number of positives and negatives. So I think of a balloon in my head is what I'm thinking about now. The bottom also has the same amount of positives and negatives. That's what makes it neutral. The charges are there. They're just evenly distributed. They're just even in amount. They have the same number of positives as they do negatives. So the same thing is true about this. So we have positive here, negative, negative, positive, positive, negative, negative, positive. So this is neutral, neutral, neutral. But what happens when I charge it? I connect a potential difference to it. This side would become, I don't know, we call it positive. It doesn't matter. But this side would be positive. In the Gauss's law, we talk about how you would determine the electric field in between these two parallel plates. We find it to be constant because it's 0 up here and 0 up here because of Gauss's law. So we now see an electric field that points directly downward. And that would be our electric field. We know that to be what the sigma over epsilon naught. If you really were concerned about that, that's from a previous video of Gauss's law. But what happens if I have a charged parallel plate, set of parallel plates, but I put some material in between them? Well, we put our positives here. But what happens is and the negative, sorry, I want to finish that off. What we find is that this becomes polarized because it's inside of an electric field. And the negative charges move towards the top, causing the top part of our dielectric material to be negative in nature. It's neutral overall, but it's negative in nature because of the polarization aspect of it. And as a result, we find that we have an electric field that is pointing downward because of our electric field, because of our parallel plates, but an electric field that is pointing upward because of our polarized dielectric material. As a result, the electric field here is less than that. So we just have E, but then we use the idea of superposition, meaning that we have multiple things acting in the same place. So we have the electric field of the capacitor acting downward, but the electric field of the dielectric is acting up. So this here is less than that. And as a result, it takes less amount of energy to put charges on this, so we can store more. And the amount that we could store it more is just a multiply of the material. So this one would have a capacitance of epsilon naught A over D. And this one would have a multiplied amount of that depending on the material, how well it can be a dielectric. Its dielectric constant epsilon naught A over D. So it affects the ability to store charge. By inserting a dielectric, you reduce the net electric field in between the plates, meaning that you can now store, your capacitance is now larger, meaning you could store more charge. The justification that you would use is that here you only have one electric field, and here you have opposing electric fields, which allows you to understand that something has changed, and that's what it was. To find the net electric field, you'd use superposition. Since they're pointing in opposite directions, it's reduced. Finally, RC circuits. I hope not to screw up too much, but I guarantee I always make a mistake doing this. I even have notes, and that doesn't always make a difference. So we're going to use the conservation of energy statement loop rule. This is different than you would have to do in an algebra-based class. In an algebra-based class, you only worry about time 0 and time infinity. And in AP Physics C, you worry about the rate at which it charges. So we know it starts with nothing and ends with everything, but how does it get there and what happens? So I begin with loop rule, so I draw my loop. And recording, okay, good. I have my input voltage, I have my voltage in the resistor, and I have my voltage in the capacitor. Voltage is going to either be here or here, and it's going to come from there. So I use my loop rule to say V input minus the voltage in the resistor minus the voltage in the capacitor equals 0. So believe it or not, that's our foundation. And anytime you see a circuit, if you're looking for a way to start, you should use one of the Kirchhoff's laws. And in this case, you want to use the conservation of energy. You want to use the loop rule. Okay. So our input voltage is just a power supply. It's a static number. It's a constant value. But where it is depends on what time we're at. And right now, we don't have any time component, but we want to know how much charge is here, and we want to figure out how much charge is there as a function of time. So we need to figure out where we're going to get Q from and where we're going to get time from. So I'm going to do a couple substitutions here. So we got our input. And then I know that the Ohm's law says the voltage in a resistor depends on the current, I, and the resistance of that resistor. That's important that we have this R. It becomes part of our time constant shortly. And then we've got the capacitor. So where did I put that? Let's just make sure we're doing that part right. I'm pulling it up from here. And that says it's Q over C, or the voltage in there is equal to Q over C. There we go. So there's our Q. That's the amount of charge on the capacitor. Hey, that's important. That's what we're ultimately going to be figuring out when that gets full. And the capacitance of the capacitor, which would be given or something like that. And that equals 0. Unfortunately, we still don't see time, and this is what turns this in from being just an algebra-based question into now a calculus-based question, or for a physics C course or any E&M course. If you want to be an engineer or whatnot in college, you would have to take the calculus-based version of this. So I have my input voltage, and I need to remember that the current is the rate at which charge moves, and what we want to do is we just want to call that dq dt. The rate at which charge moves through this circuit is dq dt, R minus Q over C. And now I've got my differential statement. So now we're going to do, we're going to separate our variables and integrate, because you need a differential equation here. I've got my Q, I've got my T. That tells me I'm doing something right. I need to get this Q and this Q on the same side, and everything else as much as I can on the other side. So first thing I want to do is isolate this dq dt, and I'm going to do that by saying V input minus, I'm going to add that to the other side, minus Q over C equals dq dt R. What I need to do then is I need to isolate the dq all the way, so I'm going to divide both sides by R. When I divide both sides by R, I get V input over R minus Q over RC, that's important to me, equals now dq dt. There's a bunch of algebra right here. The way I think about doing this next step is different. It varies from person to person, but I think about getting this Q as by itself as I can. And the way I'm going to get that Q by itself as much as I can is I'm going to factor out this negative and this RC. So I'm going to factor out a negative 1 over RC. So I'm going to pull that out of this statement, negative 1 over RC. And then algebra is a little tough here because if I factor out an RC here, I get VC. That's what I'm left with when I take an RC out of there. Plus, oops, I got to put my negative because I factored out a negative. And then I got to put plus my Q statement. And that equals dQ dt. The next thing I do is I cross multiply and divide, and I'm going to move that step up to here. And when I cross multiply and divide, I'm left with the statement that looks like negative 1 over RC dt. And that equals dq over negative VC plus Q. This is nice because now I've got myself a situation where I've isolated my variable. It's all by itself. I know it has this constant value next to it. The voltage that's provided by the battery is constant, and the capacitance of the capacitor is a constant value, but the amount of charge on the capacitor is what varies as a function of time, and it varies right there. So this would be the step where you set up a differential equation, but we didn't solve it. So that would be the set up a differential equation, and we didn't solve it. Then I'm going to evaluate this from 0 to t, and I'm going to evaluate this from 0 to q. To do that, this is nice because I just need to put that in. The t here is 0. There is no 0 value, so it's negative t over RC. But for, if they get really picky, you do that, you'd evaluate that integral from 0 to t. And then over here, what we want to do is we need to remember a trick that we learned in calculus. It's also on the back of your formula chart. And that is that the integral of this statement is natural log of negative VC plus Q. And we have to evaluate that over the bounds of 0 and Q. All right. So we're going to keep going here. When I do that, I got to do my final value minus my initial value. For my final here, I plug in t, and then I plug in 0. This minus 0 is still that. So my left side is pretty well taken care of, negative t over RC. This RC is our tau. It's our time constant. It depends on the resistance of the resistor and the capacitance of the capacitor. It changes from circuit to circuit, but each circuit will have a constant value of this. Finally, what we need to do is we need to evaluate this integral. So when I plug in my final value, I would get the natural log of negative VC plus Q minus my initial value, which is just this, but I still have the natural log statement of negative CV. Sorry, I flipped that. I don't know why I flipped that right there, but it's the same thing. Now I've evaluated that, and then there's a bunch of tricks here. It looks very similar to air resistance. It would also look very similar to inductors, LR circuits. But this year we're not getting to that, but I'm sure I'll make a video next year over this. When I take two natural logs and I subtract them, or there's a log trick. When you subtract two natural logs, you just divide them. Or yeah, that's how I think of it. I'm sure some math teacher would tell me it's a little bit more complicated than that. I flipped it back. So that's just using our natural log trick. The negative isn't from this negative. The negative is because there's a negative right there. Next, how do I undo a natural log? It's I think of it as, I call it E-it. I heard that from a teacher years and years ago. I don't know if that's a common term in a calculus class. It's been a really long time since I was in a calculus class. And what I got to do is I got to E both sides. So that means I put E and I raise it to the power of this, which undoes the natural log. So then we just do negative VC plus Q over negative VC. A long process. And then we're going to cross multiply and divide. So I got negative VC, e to the negative t over RC. That's a negative sign. Negative equals negative VC plus Q just cross multiply, and then I add. I want to isolate my Q because I want my Q as a function of time, so I add the VC to the other side. So I have VC minus VC e to the negative t over RC equals Q. And then if you really wanted to make it beautiful, you would take the VC out of this. It's in both terms. So I'll just take the VC out. So I got VC times the quantity of 1 minus e to the negative t over RC equals Q. One thing you might want to be aware of is that this VC would be equal to Q max. That would be the total amount of charge that we could put on it, because once this is full, it's going to have all of the voltage. There will be no voltage here. That means there's no current there because all the voltage is here. Its capacitance is constant. So we want to be able to say that VC would be equal to Q max, which I think is important to think about. Hopefully I have one more sheet of paper. I hoped that I did that. I do. I'm just going to take this statement, and then we're going to graph some stuff and talk about it a little bit, and then that's going to be the video. So I've got my VC times the quantity of 1 minus e to the negative t over RC, and that equals Q. This one's going to look pretty bland to start. There's nothing. I want to think about at time 0, and I want to think about at time equals infinity. We talked about it on the way. We said at time 0, the Q would be 0. Let's prove it. Let's see if we're right. This voltage would be changing as function of time. Once it reaches total VC, it would be Q max. So we plug in 0. Anything to the 0 power is 1. So when I plug in 0 here, E, so we got VC times the quantity of 1 minus e to the negative 0. Negative 0. There's a student of mine that loves that from years past. Wonderful clarinet player. Equals Q. So we have e to the negative 0. Anything raised to the 0 power is 1. So now we just have VC times the quantity of 1 minus 1 equals Q. So at time 0, we find that 0 times this is 0. Actually, I was thinking too hard ahead. My bad. So this is just VC. That's fine. So Q at time 0 equals 0. This is exactly what we expect. We're going to draw a graph here in a second. But what about time equals infinity? At time equals infinity, we still start with our VC statement. We do 1 minus e to the negative infinity now over RC. And we think about that being equal to Q. E to the negative infinity. What is e to the negative infinity? E to the negative infinity. What the heck? E to the negative infinity. E. So 1 over infinity is more or less what we're thinking about. And so we would leave ourselves with VC times the quantity of 1 minus 0, about approaching 0. This is an asymptote. We will never actually get there. You can't touch infinity. It's just an idea. So then at time infinity, it was Q at time infinity is equal to CV, which we said was equal to Q max. How does this look on a graph? So we're going to graph Q as a function of time. At time 0, that's all the way over here at the origin. It's 0, and then at time equals infinity, that's somewhere down here. It's going to approach a value of CV. So how does it? What does that look like? Does it curve parabolically up, or do we expect it to reach an asymptote? And we expect it to reach an asymptote, so it's gonna look like that. And that's a good way to think about it. What's it at time 0? What's it at time infinity? There's lots of things you could start doing here. How much voltage is on the capacitor as a function of time? What to do, I would do right there is I just divide both sides by C. If I divide this side by C, I'm left with voltage. And if I divide Q over C, looking at Q over C, where's that piece of paper that I used at the immediacy to reference? Q over C, get voltage. So if I wanted to know the voltage as a function of time, which I was alluding to incorrectly earlier, if I want to know the voltage as a function of time, just divide both sides by the capacitance. What we would find in the resistor is the resistor would just be the opposite of here. So whatever the voltage on the capacitor is, we would say, we just go back to our junction, our loop rule, and we'd say that the total voltage minus the voltage in the capacitor minus the voltage in the resistor equals 0. So if I know what this is, and I know what this is, I know what that is. So if I know this value, I don't know, it's 8. And then if I know it's 7 at this point, then I know that there's 1 there. And then if I know the voltage in the resistor, and I know the current in there, I know the resistance of the resistor, I can find the current in the resistor. The current in the resistor starts high and ends low. So it does this, but in reverse. If I were looking at it as a current as a function of time, it would start here and approach 0. Thinking about conservation of charge, where is the charge located? Is it either in the resistor or is it in the capacitor? There's other things you could look at with the capacitor. Some other questions you might want to make sure you're aware of and how you would think about is, how does this change our problem? If I have these two, and I have a series, I have 2 different loops, I guess, was how you want to think about it. And ultimately what would happen is there'd be less voltage here. And the way I really think about solving this problem out is I just actually remove that and I solve this as a series circuit. So I just think of R plus R as the total resistance. I find out how much voltage is here and I find out how much voltage is here. And then I use my ideas of parallel circuits. And if I say voltage 1 and I say this at time infinity, right? This is time infinity, and voltage 2, then this would be equal to the same amount of voltage as that, voltage 2. It's still true at time 0, there's no voltage here, there's no charge here. So then if you say that at time 0 there's no voltage here, that means there's no voltage here. So questions ask, where's the current at time 0? Oh, it's all here. But where is it at time infinity? Well, this voltage and this voltage will be the same. So the current over time for this goes down and the current over time for this goes up, but they approach the total current at time infinity. A graph real quick about that looks like the voltage in 1 would look like that, and the voltage in, or the current, this is the current as a function of time in the resistors. Just a quick way to think about it. The current in 1 and the current in 2 looks like that, where it approaches the value of V over R plus R. And this would be at time infinity. So that's something to think about. And how and if I know the current, I know the resistance, I know the voltage is just IR. So then we would say that the voltage in the capacitor also looks like this bottom one, not the top one. So just some things, some extensions to think about in the off chance that they ask those questions. I hope that you find this video informative and valuable. If you don't, that's okay. There's lots of videos on the internet. I hope you all have a wonderful day. Good luck.